Okay. So in the last class, we looked at the two-stage Miller compensated OTA. So let me quickly draw that. Okay, so this was the two-stage Miller compensated OTA. So this has one right half plane 0 and two left half plane poles. So can you tell me what is the DC gain? GM1 by GM2 by G2. Okay. So what is the first dominant pole? Huh? G1 by C1 plus? Okay, let's say this is CC. Yeah. CC into GM2 by G2. And we also saw, in most cases you can further approximate as G1 by CC is the dominant cap, so that's what will happen. What about the second pole? So first let's tell me the capacitance. CL plus C1 and CC in series, right? And conductance? GL plus? You have the capacitive division between these two times the GM of this, right? So we'll call this GM2 by C1 plus CC. And again, in most cases you can approximate as GM2 CC by C1 plus CC plus CL plus C1 CC by C1 plus CC. And what was the right half plane 0 location? Okay, like that was GM2 by CC. And what was omega U approximately if beta is 1? GM1 by CC. Okay. This is assuming beta is 1. For other values, you simply multiply beta. And again, please note, only the expression of 0 is exact. All the others are all approximate expressions, including omega U. Okay. And okay, so let's quickly write the phase also. So what is the phase at phase of the loop gain at omega U? So we'll have the contribution due to the first pole. But omega U is approximately DC gain times P1. So it's like you have minus tan inverse of the DC gain, very large quantity. So tan inverse of very large quantity is as good as minus 90. And then you have the phase lag due to the second pole and the 0. Let me write it here. So omega U by Z1, which translates to simply GM1 by GM2, right? And the phase margin was in turn 90 minus this. That's all. And in the last class, we also saw some simple design example of how we might go about designing this. Okay. And the takeaway must be that in practice you will have a lot more design variables to decide than the constraints you have. So you actually need to make some clever approximations and assumptions to simplify, right? Else if you try to find a closed form expression for everything in terms of the given parameter, you will never be able to solve it, right? And one such approximation we made was the following. Yeah, no, not that. That is one. And the second fact was that for the second pole, we assumed C1 was much less than CC, and CL was and C1 was also much smaller than CL. So in that case, what is P2 approximately? GM2 by CL here, okay, right? And I mean we took a case where we were given a phase margin omega u and load capacitance, right? Okay. Now of course once you design, if you find that your specifications are not met, you need to know what to go about and change, or if the specifications change or some parameter changes, you need to know what exactly you need to change to get the right point, right? It shouldn't be like you go to some distant relay to ohms and randomly turn on switches to see which turns on the fan. Should exactly know what button and what switch to press to actually get something done. That's the important point of design, okay? And we are looking at one such case, so let's actually repeat that and continue. So let us say we designed for some specs like this, and say the load cap increases. So what will happen? We saw that, but let's quickly do that once again. If the load cap increases, what changes? Location of P2 decreases, right? If P2 decreases, what will happen? Yeah, that's fine. These are my specs, right? In terms of the specs, what changes? Phase margin degrades, right? Because to have a good phase margin, all my higher non-dominant poles must occur much greater than the unity gain frequency. Now it is coming closer, and even mathematically speaking, you see that this fraction is going to increase, right? So the phase lag due to that will increase and phase margin will degrade, okay? So I mean this is not good, so we need to restore our phase margin. And let's say for example to get a particular phase margin, say you found out that this ratio must be some 1/8, okay? I mean I'm just randomly saying some numbers, okay? So now you find P2 has decreased, so what should you do? You need to decrease omega u, that is one option. You need to decrease omega u. And how can you decrease omega u? Yeah, that is obviously one option. You can increase CC, right? So when you increase, okay, so that's fine. Is there something else you can do? You need to to decrease omega u. Omega u depends on what? One way is to increase CC. What else can I do? I need to decrease GM1, okay? So now let's say, I mean, once you change, you should see if that affects something, right? For example, if you increase CC, does it affect anything else? Yeah, but if I mean the zero contribution is this, isn't it? If I maintain this ratio, I am set for the zero. So increasing CC actually is not changing anything that badly for us. Okay, but if I reduce GM1, what will happen? DC gain will reduce, right? Because DC gain is directly dependent on GM1. So you need to make sure when you do this, DC gain is same. Okay. So what are the thing? Look at the expressions we have. Why? Correct. Exactly. So this term, right? We assume that GM2 was much greater than GM1. So now we have reduced GM1. So is it good or bad? This is good, okay? So this is actually okay. Phase margin will improve, so that's fine. It's an added benefit, you just take it and go, right? Is that okay? Phase margin depends on the ratio of GM1 by GM2. If you reduce GM1, this term will reduce, so your overall phase margin will also increase. That's fine. Cool. But now you see in this process we have actually reduced omega u, right? And I mean reducing omega u is okay, but as I mentioned, omega u kind of determines the closed loop bandwidth, right? I mean only for large phase margin it's equal to closed loop bandwidth, but even otherwise the closed loop bandwidth will depend on omega u. So in turn it decides the speed of the op amp. Okay, so you don't want to reduce omega u. So let's say I want to maintain the same ratio without changing omega u. What should I do? Back to the same thing. This is the ratio we want. P2 has reduced, so I don't want to change omega u. So what is the only thing I can change? I again have to see if I can increase P2. And how can I increase P2? This is P2. Okay. The only way is to increase GM2. That's all. So which means I'll go ahead and increase GM2. And we saw, the way to increase GM2 is actually you go and increase both current and the width. Okay. Only this will ensure that all the operating point voltages will remain the same. Okay. Okay. So now let's say we'll take another case. Paste it. Okay. So now let's take a second case where RL has reduced. Okay. In other words, the output conductance has increased. So what does this? What will this affect? If GL increases or RL increases, this is basically GL. If the load resistance decreases, from the expressions we have, what do you think will get affected first? DC gain, right? So DC gain reduces. Let me write it here. Anything else? Right. So here we made an approximation. We ignored this guy. We ignored GL term. Now GL will also come. So is it good or bad? Why? No, we designed for this value, but see, we assume that P2 is just dependent on GM2 by CL. But now you also have a contribution from GL. It is good, right? Now your second pole has actually moved far away. It's much higher than your omega u, so that's good. So you take it and live, right? If you get something for free, don't ask. Not true always, but yeah. So your phase margin will kind of improve to some extent slightly. So this is okay, but this is not good, right? Because remember, the whole point of having a large DC gain was when you put it in a feedback with a feedback factor beta, we expect that the closed loop gain is 1 by beta, but in practice you will have beta by 1 plus beta times loop gain by 1 plus loop gain, and this in turn is basically A naught beta by 1 plus A naught beta. Okay. So you want this to be as large as possible so that the closed loop gain is tracking 1 by beta. So basically the DC gain determines the DC accuracy. So you want to restore the DC gain. So what can you do? I can increase GM1 or GM2, anything. Okay. So again, you can increase GM1, or let's say if you can't do it beyond some point, you go ahead and increase GM2. And again, to increase it, you will have to increase the current and width simultaneously. Okay. Right, so we see that the moment the load capacitance increases or the load resistance decreases, which means your load has become heavier to drive, the only reasonable way seems to be to go and increase GM2, right? So even in the previous case, that's what happened, right? We finally had to increase GM2.
By increasing GM2, we are shifting P1 still.
That is good, right? You are decreasing P1, that is okay, right? Isn't it?
But we are losing that bandwidth.
No, we are not worried about open loop bandwidth. As long as my omega u is same, I am happy. Okay. And this should make sense because even when we came up with the two-stage structure, we told that the first stage will provide the gain, and the reason for adding the second stage was what? Why did we add the second stage first of all? Huh?
So that like buffer will understand.
To drive a load, okay, we couldn't drive a resistive load, and that is why we went ahead and put a second stage, right? So this basically is for driving the load. Okay, so whenever the load becomes heavier to drive, it makes sense you go and increase that particular stage. Okay, so let's take one more case. Okay, so let's say now we have again designed for this specification, everything is working fine, and then suddenly you are asked to increase omega u. That is, you want to make the closed loop bandwidth wider. So what can you change? Okay, so before that I want to increase omega u keeping the phase margin same. Okay, that's also important, same as before. Okay? Yeah, sorry, what should you do to increase omega u first? I can decrease cc. Oops. Or I can increase GM1. These are the two things. So let's see if when we do something, we should see if that affects something else, right? So if you decrease CC, is there something that what else will change? I mean, see, if I increase CC without changing anything, the contribution due to the zero in phase is ratio of GM1 by GM2. If I increase CC without changing this ratio, there is no problem. Okay. So, so no problem from the zero as such. Okay. Okay. Yeah. So yeah, but what else will change? Sorry. P1L. Move to higher frequency. That is one.
P2 approximation.
And also here, as you mentioned, this is something we assumed, right? So two things can happen. As you mentioned, the first pole can come higher, but that could be okay because already the first pole is much at a lower frequency to start with. And the second thing is this assumption, maybe if you decrease CC so much might not be valid, so we need to take care of that, right? So P1 will change and we should look at C1 less than CC. These things you should worry. Okay, so if I now increase GM1, what will happen?
Phase margin.
First of all, you can clearly see this is going to take a hit. Okay, so phase margin is directly going to get affected. Okay, so now we have increased omega u, but we want to keep the phase margin same, right? So this is what you want now. So what would you do to keep the phase margin same? I mean, so I increased omega u, okay. So here from this, what, I mean, phase margin do you think increases or decreases? It will decrease because, I mean, now P2 is at one position, we have increased omega u, they are much close by. So you'll have to what? To keep the same phase margin, what should you do? I have to move P2 apart, okay. And how can I move P2 apart? I need to increase P2. So I have to go and increase GM2 again. So that again boils down to increasing the current in the second stage and the width. Okay. So looks like the final Brahmastra we have is to just go and burn more and more power, right? So that's the final button. So just like in Brahmastra movie for Ranbir Kapoor, the button to unlock his powers was Isha. So for the circuit designers, the magic button that solves most of our problems is to go and increase power. Okay? But of course, that might not be the best solution all the time. But it's always an option. Cool. So now let's actually try to look at the bode plot. So I'll assume we have a feedback factor of beta. So loop gain is basically beta times A of S. So I'll try to sketch the magnitude and phase here. Okay. So this is magnitude of loop gain. So DC it starts with beta I naught. So the first pole say occurs somewhere here. So it goes as 20 dB per decade. And then we have a pole under 0. So we need to find which comes first. So as we saw, the approximate expression for P2 was GM2 by CL, and this was GM2 by CC. This is not approximate, this is actually exact. Let me correct this. I mean, I'll assume that CL is actually much greater than CC. So in that case, what will occur first? P2 will occur first, okay? I'll assume that. So let's say this is my omega u. So P2 comes here, and then the 0 comes here somewhere. Okay. So what is my omega u in terms of the parameters? Omega is what in terms of GMs and capacitors? I mean GM1 by CC if beta is 1. Now I assumed some other beta, so what is it? Beta GM1 by CC. Okay, this is my omega u. Let me also sketch the phase now. So first, because of the first pole, I'll end up with a phase of 90, right? And then we have the second pole. So by the time you reach omega u, the phase will start to drop, right? And eventually, what will the phase reach? To which value the phase will reach eventually? Okay, look at the expression. Look at the transfer function. Or where is it? We have two poles and a right of plane 0. As omega tends to infinity, what frequency will it? What phase will it? Minus 270, because these two will give minus 90, minus 90. Right of plane 0 will also contribute additional minus 90. So it will eventually go and reach minus 270. Okay, something. Let's say this is minus 90, and say this is minus 180. Draw it slightly low. Okay. So now let's say at omega u, this is my phase margin, right? And let's say this is some 45 degrees. Okay, what I'll say is, let's say this is for beta equal to 1. So let's say I'm saying for beta equal to 1, I find that the phase margin is 45 degrees. Okay. And as we saw in the last class, having a phase margin of 45 degrees will result in actually a peaking in the closed loop frequency response. So what is the usual phase margin you want? Greater than 60. 76 degree if you are great, but at least 60 degree we need. Okay. So let us say you have a company, you design this op amp, and after manufacturing, when you measure, it turns out for a feedback factor beta of 1, phase margin is 45 degrees. Okay, but the everyone wants phase margin of 60 degrees. So what would you do? You will throw this op amp, or can you market it as a good op amp under some conditions? You understand the question?
Yes, sir.
The op amp is designed. I can't go and change the op amp now. For a feedback factor beta of 1, I go and measure the phase margin. It is 45 degrees. That is not what everyone wants.
We can operate in the region where it's not before that.
How will you operate it?
For omega, we look like load, if it is smaller load, it can.
Okay, let's say loads are all fixed. Okay. I mean, so here what is the statement I have made? What is the statement I made? If beta is 1, its phase margin of 45. So do you think if I change beta, something will happen? So let's say I change beta, I reduce beta. practically beta, maximum value of beta is 1, right? So I reduce beta, what will happen to these plots? Phase plot will remain same, magnitude will basically scale accordingly, right? So we will do this something. Now my omega is this, right? And what is the phase? That's actually much better. Okay, so you can get actually a better phase margin. Okay, so the takeaway is for these Miller OTAs, or in general, I mean here, what can you comment about the phase response? Huh? No, I mean in general, if you look at the phase response, it's monotonically reducing, right? For continuously reducing phase for Miller OTAs, wherein you have monotonically reducing phase. So beta equal to 1 is the worst case feedback factor. Okay. For phase margin. So if you actually design your Miller OTA for a particular phase margin for beta equal to 1, for all other values of beta, the phase margin will be much better. Okay, so this is the usually we test it with beta equal to 1, so that you will get the worst case performance. Okay, so now let's we have looked at this stuff at block level for some time, though we'll go ahead and see the transistor level implementation. So again, to refresh your memory, oops, where did it go? Yeah, the first stage here takes in a differential input and provides a single-ended output. So what can I use for the first stage? The diff amp we saw, 5 transistor amp, and the second stage, so common source. Okay, so let's make that. So let's start the first stage. So do you want to have a NMOS stage or a PMOS stage? I mean, why? I mean, it's not a question, just a choice. Okay, so let's start with NMOS. I mean, you can have the PMOS also, right? There is nothing. So this is the NMOS diff amp. So you have a tail current source. At the top I have a PMOS current mirror. Great. So this is first stage. So let's say this is M0, M1, M2, M3, M4. So second stage is a common source. So now again I have two choices. I can have NMOS stage or a PMOS stage. So what do you think we can use? Why? So first is NMOS, you want next to be PMOS. Okay, so let's say we have two options, right? Now we can have an NMOS stage, or I can go and put a PMOS. This will be a PGD, right? So let's say I take only the diff amp here. So nominally, what do you think the DC voltage at this point will be? Huh? No, DC operating point. I mean, if both the inputs are same, we looked at it, right? Huh? So let's say this is carrying a current I0. VGD minus VSG of M3, okay, at a current I0 by 2. I mean, we remember if we told that if both these voltages are equal, even these two voltages have to be equal. We saw by contradiction, and this voltage was basically, I'll write it separately maybe. Where would I write it? Okay, I'll write it here. So this is VDD minus VSG of transistor M3 or M4 at a current I0 by 2. Now let us say the second stage common source is biased at a current I2. So what would be the required voltage here? I mean, just gate to source voltage at a current I2. No trick. Okay. So here again, let us say a PMOS stage biased at the same current. What would be this voltage? VDD minus VSG at a current of I2. Okay, so this stage naturally provides this voltage, and if you were to have a second stage for NMOS, this seems to be the voltage needed, and for PMOS, this is the voltage needed. So now what do you think is a better choice? PMOS, right? There is no harm in using an NMOS, but you need to actually make sure the levels are compatible. But if you have a PMOS, that's naturally, compatible. That's all. So if you start with an NMOS stage like this, NMOS diff amp, you have a PMOS as the second stage. And if you had started with a PMOS diff amp, you will use an NMOS second stage. So here I'll have a PMOS. Okay. So at the bottom I'll have a current source. I'll realize that also as an NMOS transistor. And this current I can mirror from this guy. So this is M0. Let us say M5 and M6. So this is the first and second stage. So we need to compensate. Where do I put the capacitor? CC. I should put the capacitor around the second stage, right? Between input and output of the second stage. Between gate and drain of M5. Okay. And this is my CC. So this is output. So first let's find out the operating point voltage. So what do you think will be the operating point voltage at the output? VSG of M5 is this, right? That is the gate voltage. No, but it's DC, right? For DC, capacitor is not there. Open. I mean, when we are looking at the swing limits, remember what I told? The drain voltage should be usually set by some gate to source voltage, or it should be set by some other mechanism. Right here, is there some gate to source voltage that will fix the drain voltage? No. So what do you think will happen finally? So this op amp, where are we going to use this op amp finally? In negative feedback. Okay, so remember, let's say you have a unity feedback. We'll put it like this, right? And this one I'll actually have to connect a bias voltage VCM, which means this will also be at VCM and the output will be at VCM. So what is setting the output common mode? No, here how did I say that? I mean, see, I applied the bias voltage here, VCM. How did you say this was also at VCM? Virtual ground. What is enforcing the virtual ground? Yeah, high gain, but something else is doing. No, just having a high gain doesn't imply virtual ground. What I am doing here, I am putting in negative feedback. The act of putting it in negative feedback is what fixes this to be at VCM, and the output will also be at VCM. Okay, and I mean, even if you have a non-unity feedback with some resistors, I think we again saw it during some slew rate calculation. This will be at VCM, this will be at VCM, and here also you connect it to be at VCM, so that without the signal there is no current flowing. So that will enforce this voltage to be also at VCM. So the important point is the output, which is the drain voltage, the bias of that is set by the negative feedback, okay, and this negative feedback must be active at DC. Because we are looking at DC biases, we need to have a DC negative feedback to set the bias voltages, okay. And in this case, the bias voltage is the output common mode, okay. This is actually very important because even if you have oscillators, for oscillators, do you think we need positive feedback or negative feedback to oscillate? We need actually positive feedback for oscillations, but even there, for DC, we need to ensure we have a negative feedback, okay. Only then the transistor's operating point bias will be set. At DC, there should be a negative feedback, and only at high frequencies you should have the positive feedback, okay. Again, and for the same reason only, this you might have seen, right, this circuit. What is the circuit? It's an integrator. So if you have an integrator like this, at DC is there a negative feedback? No, right? Capacitor is open, there is no negative feedback. So obviously this voltage will not be set. This is one of the reasons why you don't use integrators in open loop. Okay, you'll always find that this is part of some big system which has negative feedback globally. That global negative feedback is what will set all these bias voltages and make the integrator function as you want. Okay, so here, as we mentioned, we need to have this negative feedback. So let's try to quickly make the feedback. So this is my output. So I have two inputs now, A and B. So what is the negative terminal?
B.
Why? Okay, so let's see, right? If I increase B, what will happen to this voltage? It will, from gate to drain, there is an inversion. Remember, common source gain is minus GMRD, right? So if the gate voltage increases, the drain voltage decreases. So which means this voltage decreases. So what will happen to this voltage? Do you understand the logic? From gate to drain, there is an inversion. Okay. So if I increase the gate voltage, the drain voltage drops. That basically drops the gate voltage of M5. So what will happen to the drain voltage of M5? It will increase, right? So is this the positive terminal or negative terminal? It's a positive terminal. Okay. So this is my positive and B is my negative. Sorry, A is the negative terminal. This is my negative terminal. So to connect the negative feedback, I will have to make a connection like this. And here I'll have the bias voltage set. So we also saw the range of the common mode that you can apply at the input, right? So what do you think will be a reasonable choice for this input common mode? We saw a range of voltages, but what do you think would be a reasonable choice generally? Right, because we are operating from 0 to VDD. The common mode is the bias voltage. Over and below the signal, small signal is going to lie. So logically makes sense you pick somewhere closer to the middle. So the usual choice for VCM is VDD by 2. Okay. And it need not be the case. We have a range of voltages, you can pick anything in between, but this is usually a reasonable choice. Okay. Let me take it. Okay, so now can you tell me what will be the output V out common mode? VCM, that's we expect it to be at VDD by 2. Okay, this is what we expect, right? So let's see what happens. Now let's say this second stage is biased at a current of I2. Now where to iterate? Let's say this is I2. So if I call this voltage as some V1, let me mark it here. So what do you think V1 will be equal to? If M5 is carrying a current I2, what can I say about V1? VD minus VSG of M5 at a current of I2. Fine. Now when I just had the first stage like this, and when I made sure that the two gate voltages were equal, so what can you say about V1 and V3? They are also equal, right? So I'll make that statement also. If the gate voltages of M1 and M2 are equal, V1 will be equal to V3. And what is V3? Let's say this current is I0, okay? So VDD minus VSG3 at a current I0 by 2. Fine. So now obviously, I mean, looks like V1 can take two values, and I can choose VSG5 at a current I2 to be not equal to VSG3 at a current I0 by 2, right? It's a free world, so I can make sure these two guys are not equal. So looks like V1 can take two values, isn't it? So what do you think will finally determine V1? This connection is there. Huh? No, they cannot. I mean, I can choose the VSG is different, right? Sorry? M4. No. Without going to details, looks like I can have two different values for V1, right? Set by two different constraints. So which do you think will finally decide V1? Current through M5 is what will decide, right? And the current through M5 is determined by this current source, which is fixing it at I2. So what will be V1 be? It will be this at a current I2. Simply because I am forcing a current I2 through it. At least, I mean, I am going in the reverse way, but this gate voltage should correspond to a current of I2. Okay. It's not as though I am pumping a current I2 and the voltage is developed. I am going in the reverse way, but I guess you get the point, right? This should be it. So if this is the case, you see that V3 is not equal to V1. So what comment can you make then? Yeah. I mean, see, we saw that if the gate voltages of M1 and M2 are equal, then V1 will be equal to V3. Now I find that V1 is not equal to V3. So what can be the logical conclusion? Gates are not equal, that's all. Okay. So which implies gate voltage of M1 VG2. So what can you say about, I mean, remember VG2 or VG1 is same as the output voltage, right? This, we are making this connection here, right? I am setting VG1 to be at VCM, sorry, VG2 to be at VCM. So Vout need not be equal to VDD by 2, right? And in fact, this will be VDD by 2 some delta V. Okay. So it looks like there seems to be some offset between its input terminals. Okay. And this offset is called systematic offset. So because as we will see later, there is something called random offset that is not under your control. but this is something under your control, right? Because of your design choice that these two source to gate voltages are not equal, your V1 is different from V3, and that is implying that you have some offset. Okay. So now can you actually tell me a rough estimate of what this offset will be? Or if I put it another way, if there is zero offset between this, V1 will be equal to V3, right? So in other words, with delta VOS 0, V1 will be V3, that's equal, right? Now with finite delta VOS, V1 is V3 plus some delta V, right? And the delta V is basically the difference between the source to gate voltages, right? This guy. So plus this is VSG3 at a current I0 by 2 minus VSG5 at a current I2. So this is my delta V. Okay. So I see that if there is some finite delta VOS, the output increments by delta V, right? Yeah. So what will be the? Can you relate delta VOS and delta V then? No, I see that if there is zero delta V, the output is at some common mode, I mean some required voltage. Now there is some finite delta V at the input that results in a finite delta V at the output. So what is the relation between the delta V's at the input and output? No, why will they be equal? GM 1 times? Sorry? That is the current, right? See, the question is simple, right? I am applying a delta VOS at the input. This is the input. What is the output delta VOS? Into gain, right? That's basically the delta V input. Oops, sorry. The output delta V is the input delta V, which is delta VOS times the gain of the first stage. That's all. And the gain, you know, what is it? And this is all assuming all the delta V's are small. If the delta V's are all small, I can use small signal approximations, and that's how we can quickly estimate. Okay. Does it make sense? Let me just quickly say, see, without any offset, you see that V1 should be equal to V3. That's what you expect. But now you find that V1 is V3 plus some small delta V. And we saw that this delta V corresponds to differential delta V at the input also. I am just finding the relation between the delta V at the input and the delta V at the output, which is related by the small signal gain, and you know what that is GM times some R out. Okay. So now the systematic offset is obviously something we do not want. So to prevent this systematic offset, what can we do? What should we do in our design so that we don't have this offset? I2 is equal to? That we cannot ensure. Is there something that, I mean, if you look at the argument, much simpler, right? What was causing this offset here? Yeah, V1 is not equal to V3, and why is V1 not equal to V3?
V1 has two different.
Correct. Basically the problem was V1 seems to have two different values. So what is the simplest way to make this go away?
Make both the values same.
If I make both these guys equal, then there is no problem. See, the issue is this voltage is fixed by the current flowing here, and you want this voltage to be equal to V3, right? So you make sure that VDD minus VSG5 at a current I2 is same as VDD minus VSG3 at a current I0 by 2. That simply boils down to choosing these two source to gate voltages to be same. Okay. So the bottom line is, to prevent systematic offset, We need to choose the source to gate voltage of the transistor M5 at a current I2 to be same as the source to gate voltage of M3 at a current I0 by 2. And I mean, in general, what is VGS minus VTH in terms of the transistor parameters? Root of 2i by mu n Cox W by L, right? So if you want to have the same gate to source voltage, or for a PMOS source to gate voltage, what should be same? I by WL must be same. Okay, so I by W by L for the transistor M5 must be same as I by W by L for the transistor M3. And usually if you choose L5 to be L3, so that simply boils down to the ratios of the widths. I mean ratio of current to the width. That must be same. And I mean this factor has a name. This is called the current density. I don't know if you are aware of this. So the ratio of current to the width is often called the current density. So the point is to avoid the systematic offset. If we have the same lengths, you keep the same current densities for the PMOS transistors, right? So this all these three should have the same current density. If you don't have it, you will have the systematic offset. Okay. So yeah, so let's stop here.